Hey guys, welcome back to AP Physics C Mechanics. Today we're going to be looking in Unit 1, Lesson 6. So this is going to cover both projectiles and relative velocity. I'm actually going to make two different videos because they're kind of two really different topics. They're both shorter, so we're doing both of them in the same quote-unquote lesson, but I'm going to make two videos, that way the topics are separated. So diving right in, this is Chapter 3 in our textbook, Section 5, over projectile motion. And projectile motion is simply two-dimensional motion going in both the x and the y direction. But the parameters that define projectiles is that they have an initial velocity, and after they are given the initial velocity, the only thing that affects the path is gravity. And the path that it follows is called its trajectory. So for now, we are going to be ignoring air resistance or friction or curvature and rotation of the Earth, all of that stuff. The only thing we're going to be focusing on is the gravity itself. Since the only thing affecting the motion is gravity, our acceleration is only going to be based on gravity. A is only based on gravity. Sorry, trying to write and speak doesn't work out well for me. Okay, so mathematically, our acceleration vector, we're only going to be dealing with two-dimensional motion. Okay, projectiles are only going to move in the x and the y, where y is vertical and x is horizontal. So we're only going to be using our I and j vectors. But the acceleration for all projectiles is 0 in the horizontal or I direction. That's horizontal. But our gravity is always going to be in the vertical direction, or the j. So there's several options here, well, two options here with the vertical, and you have to pick every question. So I like to always choose my j direction to be going up. Okay, so that would be positive goes up, which means gravity going down is always going to be negative 9.8. We know gravity, acceleration due to gravity, equals plus or minus 9.8 meters per second squared. I'm going to leave it as g most of the time so we don't have to deal with rounding issues. And I just like working with the letters better. Guess I'm kind of weird that way. So you have to choose in your question which way you want the j unit vector to point, if you want the positive to be up or if you want the positive to be down. I am, for convention's sake, always going to choose positive is up. In every question I do, I'm going to consistently do it that way. If you don't want to do that, that's fine. But no, that's what I'm doing. So as you watch these videos, up's always going to be positive in my world. So I'm going to go ahead and make a new slide with just that acceleration function with no annotations. We've got acceleration for all projectiles. This is general for every projectile, is 0 in the horizontal, minus, for me, g in the j direction. Also, I forgot, I do this all the time. You can write your unit vectors with hats, or you can write them with the arrows on top. I was using hats last time, so I'll switch to hats. Consistency is key, and I'm not quite always consistent, so my apologies there. All right, so now that we've got the acceleration vector down, we can find the velocity vector. So to find velocity, we are going to integrate our acceleration vector with respect to time. And if you remember, whenever we integrate, we're just integrating each piece of that vector. So we're going to integrate the whole thing, 0, I, minus g, j. And that is with respect to time. So just like you do with regular integration, we're going to integrate each piece separately because they are added together. That's the rule for integration. So our velocity vector becomes the integral of 0 I hat minus the integral of g j hat. Now really, oh, and those are both dt. I forgot my dt's. Give me a second. All right, there we are. We've got the dt's. So now we've got to integrate those. Some of you may be tempted to leave out the 0 times I hat because that is simply 0. And when you get rid of the 0, it it doesn't matter because it's not adding to anything. But your motion is going to have that component eventually in the x direction, the horizontal direction, even though it's not accelerating. So I keep it there as a placeholder. That way when you integrate, you'll start seeing some values fill in with the I hat. So let's get that. Velocity equals the integral of 0. So the integral of 0 is actually not 0. The integral of 0 is 0 plus a constant of integration. So we've got 0 plus c, and we'll do that c in the x direction. You can actually notate this really however you want. A lot of times you'll see like c1 or c2. I'm going to say this is the c for the x direction, and that is all multiplied by I hat. And then we're going to subtract the integral of g times j dt. The integral of g with respect to t is g times t plus c in the y direction, and that's going for j. Now technically, when you're doing your integrals, you have to integrate everything that's in there. So you would also be integrating your I hat and your j hat, but the deal is our directions, I and j, are not changing with time, so we don't have to do that integral. Later on, when you get to college and you're doing circular motion, really in detail, you'll have to start integrating your unit vectors if you're doing polar coordinates. So just be aware, we should be integrating the I hat and the j hat as well, but since they're constant, it doesn't change, so the integral isn't affected by the I or the j. So we've got this here for our velocity vector. And we need to figure out these c values before we can move on. The c values, as you should know from our previous session, c values are simply the initial values. So the initial velocity of I in the x direction, so this would be v naught in the x direction, I did it again, vector not a hat, there's a hat, minus g times t plus c in the y direction. That's the initial velocity in the y direction. So that's v sub 0 y j hat. All right, now that we're here, I have noticed, and you might have, probably not, but you might have noticed an issue here. The issue here is with our negative. So our negative right now is being distributed to both of these terms. Which is not necessarily how it should be working out. So we're going to go back to the beginning of this, and we're going to move that negative to inside the integral. Okay, so this is plus negative g times j, which means this is going to become a positive, and this is going to become negative gt. This is positive, this is negative. We're going to move it back inside. That way we don't also have to flip the sign of our initial velocity. So now we're starting fresh on our velocity vector. We have figured out what it is. Now we're going to go find the position vector. The position is r, and that's the integral of velocity dt. So we're going to have to take the integral of v naught x in the I direction plus negative gt plus velocity naught in the y direction times j. Got too many brackets there. So now we have to actually do that integral. We'll split it up into r equals the integral of v naught in the x direction I dt plus the integral of negative gt plus v naught y j direction dt. So now we're taking these integrals with respect to time. Our velocity naught is just a constant. It's only at the beginning. It's not dependent on time. So we just multiply it by time to get the integral there. So we've got v naught x times t, and then we've got to add our constant of integration plus c times x. Now this is not going to be the same c times or c sub x as earlier. This is a new one, completely different than before. And that's in the I direction. Now I've got to integrate the other side, plus the integral negative gt. The integral of negative gt is negative 1/2 gt squared plus velocity naught in the y direction. Integral of that is velocity naught in the y direction times t Then we've got our constant of integration again, this time in the y direction, and that's times j. So if you look at this, this looks suspiciously like some of your kinematics equations in there. This is how they're derived. But let's go ahead and put in those constants of integration. Your position vector equals velocity naught in the x direction times time plus your initial position, that's r naught in the x direction. I'm actually going to change that notation there, r naught in the x direction. We're just going to make that your x naught, your initial x value. And that is all I in the x direction. And then that is plus 1/2, or negative 1/2, my bad, gt squared plus v naught in the y direction times time plus c is going to be our initial y value, that's times j. So there is your position function. It came from our generic velocity function, and this will apply to every single projectile. All projectiles that you could possibly have will follow this exact formula. So the next thing we need to talk about is how to find the velocity naught in the x and y direction. And we're going to have to do that using trig, because projectiles can be launched off at angles rather than simply horizontally or vertically. I mean, the horizontal and the vertical could happen, but we're mostly going to be dealing with the more complex option, which is at an angle. So when it's at an angle, we'll call this angle theta. It could also be alpha, beta, phi, phi, if you want to call it phi, whatever. It could be any Greek letter for the angle. I'm going to call it theta. So to find your initial velocity in the x and y direction, you're using trig. I'm going to assume you guys know how to do this, or I'm not going to assume, I'm going to show you. But if you know how to do the trig here, then just fast forward a little bit. So our velocity naught is going off at an angle. It's going to change due to our acceleration later, but this is just the initial velocity naught. So in the x direction, you have to find that horizontally from this right triangle. So that's the velocity naught in the x position. So the trig there, since this is the adjacent and this is the hypotenuse, is going to be cosine of theta. So our cosine of theta equals adjacent over hypotenuse. The adjacent is the velocity naught in the x direction, and the hypotenuse is just velocity naught. So to find our velocity naught in the x direction, you've just got velocity naught times cosine of theta. If you wanted to find it in the y direction, you just use the other trig function, v naught sine of theta. Now the cool thing is you could go ahead and take those and plug them into our general equations. So you would get the following. Acceleration is still 0 in the I direction and negative g in the j direction. Your velocity now becomes v sub naught cosine of theta in the I direction. And then we've got plus, for the j direction, negative gt plus v sub naught sine theta in the j direction. And then when we integrate it again, we got v sub naught cosine theta plus, or sorry, times t, plus our initial x value, and that is in the x direction. And then that was plus negative 1/2 gt squared plus v naught sine theta times t plus y naught in the j direction. So now we've only got this as a function of the velocity naught and the angle for when you know those, rather than the x and the y components of the velocity naught. So these are like the really general equations that you need for projectiles. And you really need to know how to go from the acceleration all the way to the position. And that's a derivation that you need to be able to do that AP could potentially ask. So once you've got these, you can solve all sorts of things for projectiles. I'm gonna leave that up to your big brains that I know that you can use. In order to find the total magnitude of a velocity or the total displacement or something, you might need to use Pythagorean theorem on your two components. So for example, if it wanted you to find the total velocity, you'd have to take each component. So for example, this would be your x component and this would be your y component. Get their values. To do Pythagorean theorem and find the total velocity, you do this squared, and then take the big square root. Or if it needed you to find an angle, you could do the inverse tangent of the opposite over the adjacent, and those components would fill in as the opposite and the adjacent depending on the angle you were measuring, if it was relative to the vertical or relative to the horizontal. Okay, so that is projectile motion. Try to work the problems on this. If you're struggling, let me know. The graphing for this is pretty much the same projectile motion graphing you've been doing for a long time. So I'm going to assume that you've got it. And if you don't, you can always ask, and I'll come help you out.